So first things up here, this is what we saw yesterday. You don't have to write any of this down. It's just kind of an introduction. In order to get a cone, or excuse me, to get a circle, why it is a conic section is because if we slice our cone horizontally, okay, straight across, we get an exact circle. Okay? If we slant it a little bit when we cut it, then we get kind of the elongated circle, or what we called ellipse. Okay? All right, so the next question it has on here is what makes a circle a circle? So I want to ask you guys that. What properties do you know that something is a circle, this very unique and special shape, because it possesses these qualities? Matt?
The distance from the midpoint is always the same.
Okay, so he says the distance from the midpoint is always the same. I'd like to change a piece of the vocabulary, but you're right. Do we call it the midpoint? Helen? The center. Okay, so he says the distance from the center is always the same. When you wanted to draw a perfect circle in geometry, what did you do? You used a compass, okay? Because what did the compass provide for you? A center point, right? That you either had like a little pointy end on your compass, or if it's the flat ones, you like held down the center. And then a set distance from it, which you stuck your pencil through and drew the circle, right? Okay. So that's exactly how a circle is defined. Okay. So this is how you would draw it with a compass. Okay. So our radius is our set length, okay, from the center to any point on the circle. And we'll write explicitly out the definition and stuff later. 22. Should be like your back cover. All right, so now that we've seen what a circle is, we want to make sure we put that in our notebook. And this is going to go on page 2. Okay? Yeah? Okay, so in your book, the front inside cover is page 1. And then next to it's page 2, and then it keeps going. 3, 4. Okay. See, number each page after this, front and back. All right. Well, I hope I've clarified. All right. So on page 2, we're going to start talking about circles. Now, the information you see up here is half of the page, and then we're going to put a graph on the bottom half of the page just so you get an idea of how much room you need. Okay? All right. So exactly what Matt said, kind of in his own words, how we define a circle is the set of all points that are equal distance from the center. So you identify your center, and then you find all the points that are the same distance from the center. Okay? No, this is the top half of the page. And there's a graph in the bottom half. So question for you guys. Yeah, Dylan? No. All right, can you guys figure it out quietly so we can keep going? All right, so we have this definition of a circle. It's the set of all points that are equal distance from the center. Okay. We have this little picture then. We have a center. There's all these points surrounding it that are the same distance away. And then that gives us this equation right here. Does anybody have any ideas? Here's what I want you to do. In your groups, take 30 seconds to a minute, and can you decide how they possibly came up with this equation of a circle given the definition? So if they said, okay, a circle is going to be this object where if you pick a center, it can be all the points that are the same distance from the center, then how do they decide that the equation should probably look like this? All right, I hear people that have discovered some things, so who wants to share with us what we know? Eric, did you have something to share with us? It's the distance formula. So notice that they've changed some of the letters or some of the representations of points. But if we took the picture that we have up here, and we said, okay, because it's a circle, they claim that the radius doesn't change, right? The distance from the center to the point stays the same, and we call it a radius. So if I plugged that information into the distance formula, and you don't have to write this, but just to kind of see how it works. I'm going to call this r squared because we call that distance in a circle, or r, not squared, because we call that distance in the circle the radius. And notice the points we would be measuring the distance between is this point they called hk and the point that they called xy. And in the distance formula, we're looking at the difference between our x coordinates and the difference between our y coordinates. So if we take one x coordinate and subtract the x coordinate of another point we're measuring between, one y coordinate and subtract the y coordinate of another point that we're measuring between, this is our distance formula to measure the radius of the circle. Now, this doesn't look exactly the same as this. What did they do to each side? Square it, okay? It's essentially the same idea. It just gives us both ends of the circle instead of just one part of it, because we can then, when it's squared, we have the positive and the negative, and it's nicer to look at, right? Okay. All right, so if we were going to build an equation with a circle that has a center at these coordinates and a radius of 0.25 units, what would that equation look like? Matt? Does everybody see where Matt got this from? He's taking the equation of the circle. Okay? To write an equation, we still need our x and our y variables involved, but we're using the center as kind of the h and k variables in the equation. Right? And our radius is our r, and in our equation, we like to have r squared. Okay, so that's where the 0.125 is coming from. So a couple of things. If somebody gives me this information, I can write this equation. If someone gives me this equation, I should look at this equation and I should think, what conic section is this? And what conic section is it? Circle. How do I pick out the center of the circle? The h and the k. How do I know what the radius of the circle is? Helen? Take the square root of the r squared. If you know the center and the radius, could you plot the circle on a graph? All right, so that's what we want to do next. Okay? So in the second half of this page, we're going to graph this equation of a circle. So again, how do I look at this and know? Because, okay, this is the annoying thing about your textbook, so I organized it a little differently. They give you all the really easy problems in each section first, and then the very last section of the chapter, they put the hardest version of every problem and put it all together. So we don't do that. Because then what I found by doing that is like you guys feel all like happy about conic sections. And then we learn the last section that's closest to the test. And everyone's like, oh my gosh, now I don't know how to do conic sections. Okay? So what we want to do is when we're learning about circles, we want to be able to do from the easiest to the hardest problem about circles immediately so that we don't think we know about circles and then all of a sudden someone makes it harder 2 days before the test or something like that. Okay? So just know that your homework's going to be weird because it might have homeworks from the circle section and then homeworks from the last section of the chapter, but that's because we're doing it all together. Right? Now, this is what I would call a nice circle equation. Okay? So first of all, I look at this. How do I know it's a circle equation? Raymond? Good, because it's the distance formula. So it fits that specific format, which tells us this is a circle. And as we learn each object, we're really going to think in our head how to differentiate between the two. Given that this isn't only, like, it's not only the distance formula, it's written exactly how you'd want it to be written, right? Okay? It's like all set up all nice and perfect. What's the center of this circle? Sorry? 5, -2? Good, -5, 2. Okay? So remember our H's and K's when we were doing translations and stuff like that? How we always took the opposite of the horizontal one? This is kind of the same case, and you do it in both cases because the x and the y are on the same side. They haven't moved it to the other side, so it affects like the signs of the different objects. Plus, in the formula, it was x minus h and y minus k, so we would want to use the opposite signs. What is the radius of this circle? Raven? Good, rad 3. And let's say I'm doing this without a calculator. We should be able to approximate the square root of 3. What do you guys think? 1 point. I only need one number after the decimal place. Well, decide. Do you think it's closer to 1 or closer to 2? 2. Closer to 2. So you should pick 1.7. Sure. Okay. All right. And I won't judge too harshly with your approximations because I don't want you to spend time multiplying it all out. But I would expect you to know exactly what you guys just decided. That the square root of 3 is between 1 and 2, and it's closer to 2 than it is to 1. That makes sense? All right. So to graph this, go ahead and in the second half of this page, this is the last thing you have to fit in there, graph this circle. So you have the center, you have the radius. See if you can get what this circle. I'm especially sorry to those of you that had Miss Hoffman because she's so lovely at her drawings, and this is what you get now. Okay. So we have our center, we have our radius. That should be enough to plot our circle on the graph. Okay? So why we started with the circle instead of the parabola, opposite of what your textbook did, the equation is almost just like the distance formula. There's only 2 key pieces of information to get it to graph. So if I had to rate it on the scale of easy to hard, and again, that's all subjective, I would say that this is probably the simplest conic section because it has less parts forming it, therefore less information that you have to pick out. Okay? All right. On page 3, we are actually going to do 3 examples. Okay. I would say this example can take the first half of the page, and then the other 2 can split the bottom half of the page. Okay. So I would think of page 3 like this, since you guys are all crazy about your organization. Example number 2 can be like in the top half, and then example number 3, and then example number 4. Does that put your mind at ease and you feel okay now? Monet, are you good? Are you good? Okay. All right. Now, the instructions in example 2 say graph the circle. So if I'm smart enough to read the instructions, I know that I'm supposed to be graphing a circle. However, I am not as nice as those instructions because it's not always as explicit as that once we learn more than one conic section. So we have to be able to look at this and understand how we would even know that we are graphing a circle given this equation. So look at the equation. I don't know, looks kind of crazy. Okay. How could you identify that this is a circle versus any of the other objects that we've graphed in our class so far? Eric? Okay, so as of right now, it's the only thing that we've studied where both x and y are squared, right? Is that okay? So that's your red flag that this is a circle. Is it set up in a way that you can pick out the center and the radius to graph it? Okay, what's the center of the circle? Yeah, I don't know either. Okay, Matt?
Didn't we just learn that ellipses have x and y squared?
Okay, good. So if we paid attention to yesterday in our introduction, ellipses do have x and y squareds also. So let's do this. We're going to look at parabolas tomorrow. We know they're a little different, and then ellipses starting next week. So right now, the way we differentiate this as a circle is it has x squared and y squared, and we haven't technically done by ourselves any graphs of any other conic sections. But we do know that there's a big, red flag coming up even with that, right? That ellipses also have x squared and y squared, and there's going to have to be a way that we differentiate between a circle and an ellipse. If we don't know the answer to that question right now, it's okay, but that question can't leave our mind. Because in the end, when an equation is thrown at you and I ask you to graph it and identify certain parts, I'm not going to tell you if it's a circle or an ellipse or whatever. That's up to you to know. Okay? So right now, you can grasp onto the fact that circle has x squared and y squared, but like Matt said, you better pay close attention in the future because so did an ellipse, and we have to be able to tell them apart. Okay? All right. So nobody could identify for me the center and the radius of this circle right now as it sits like this. Okay? So then my question to you is, How am I going to get this on the graph? How am I going to find that information? Julia? Okay, so she's saying to factor it. Does that make sense to people? Look back at the format of the equation that we wanted. We wanted something like this. X minus h squared, y minus k squared, and r squared. Right? So we want to get these factors, one factor that contains x, one factor that contains y. They aren't just factors. What kind of things are they? Albert? They're perfect squares. So I don't just want to factor some polynomial with my variable of x. I want it to factor specifically as a perfect square if I want to easily be able to pick out the center of my circle. So look right now, if you just tried to factor what you have there, x squared minus 12x plus 84, is that going to factor as a perfect square for the x's? No. Okay. Could you do something to make sure that x squared and whatever else goes with it could end up factoring as a perfect square? What could you do to guarantee that? Minshao? Completing the square. Right? So we can complete the square and then guarantee for ourselves a perfect square. However, that kind of demands that we add in our own values to the equation, so we're just going to have to be really careful about doing it technically correct, so that when we add values in, we're adding the right values and we're kind of balancing the equation as we do so. Okay? So this means we want to complete the square with an x group. We want to complete the square with like a group of y values, and then we want to end up with this like number on the other side that represents our radius. So the first thing I'm going to do is organize the equation in a way that that's possible for me. So I want x squared and minus 12x together. That makes sense. Okay. What do I want on the same side of my equation as this x group that I want to make a perfect square? What else should be on that side? Alex? Yeah, the y's also, right? Because I want them to also complete a perfect square on the same side of the equation as my terms that contain x. Right? So I'd like to make a perfect square out of what's going on right here. But then I'd like to also make a perfect square on that same side of the equation out of the y values. So I'll go ahead. Okay. Yes, they are different signs because I moved them from the right side to the left side of the equation. Okay. And is 84 the number that completes any of my perfect squares here? Is 84 a perfect square? No. So for right now, 84 just has to be on the other side. Don't freak out that it's negative yet. Yes, if you end up with a negative, that's kind of crazy that r squared would be negative. That doesn't make sense. But we're going to do a lot of stuff to this before we're done and have our equation in the form we want. So no freaking out yet. Okay? All right. You guys go ahead and see if you can finish completing the squares to get your equation in this format here. Okay, let's see. New volunteers. Tell me how you went and completed the square. Allison.
We would do b divided by 2 and then square it.
Okay.
So the first one it would be 12 divided by 2 and square it, which would be 36.
Good. So 36. Okay. What else, Claire?
Then we did the same thing with y and that 64.
All right. Julia?
And then because you added 36 and 64 to that side, you have to add 100 to the other side.
Good. So she's saying add 100 here, and this is representative of both the 36 and the 64. All right, good. Okay, so we remember our completing the square. We remember balancing our equation. And remember, this can get complicated if there's another factor in front of here also, right? Because then it wouldn't just be 36. It'd be 36 times whatever's here and get a little more chaotic. All right, so then if we factor this, we have x minus 6 squared, y minus 8 squared equals 16. Well, that's a nice number. All right, so tell me what I need to know about my circle in order to get it on the graph. New people. This isn't the hardest question I've asked you all day. Come on. Monet. Okay, so we have a center at 6, 8. And, Raven? Our radius is at 4. So go ahead and graph your circle with its center at 6, 8. I'm going to number my graph by 2s, okay? You can do the same. 2, 4, 6, 2, 4, 6, 8. Okay. All right, so our circle equation can come nicely packaged or not so nicely packaged, but we can manipulate it to be what we want with the skills we have prior, and then we can use the equation once it's in that standard form to graph the circle. Okay? Any questions about graphing the circle, rewriting the equations? Yes, you're going to have to know the circle equation. Then there's also going to be an ellipse equation, a hyperbola equation, a parabola equation, and some minor equations associated with those. So I'm telling you ahead of time, not to make you anxious, even though it might just a little bit, but to let you know that there are a lot of things you're going to have to know about each shape as we move through. Okay? All right. The next thing I want to do, and again, I'm going to give your guys' groups a couple minutes to think about this. Write the equation of the circle that passes through -4, -5, and has a center at -9, -12. Okay, so you have a key piece of information. What would I consider a key piece of information up here for our circle equation? Grant? Good, the coordinates of the center. Key, right? Totally something we can immediately plug into what we want. But they didn't just hand us the radius, so there's a little more thought that we have to put in this here. So take a couple minutes with your group, see how far you can get with this, and then we'll look at it together. Okay? All right, let me hear your brainstorm. So we have a center. What were your ideas about completing this equation? Jordan. Good. Okay, so we said you could use the distance formula to find out how far it is from that center to that point. Because remember, what they're giving you is you have some center, you have some point on the circle. The distance between them is going to be your radius, and that's the other piece of information you need for your equation. How many people used that approach? All right, did anybody do anything that they consider slightly different? That's, yeah, Helen? Good. Okay, so Helen says she took just the circle equation, right? But let's think about it. The circle equation is really the same as the distance formula. So she did what you did. But I would argue that her way is a little bit simpler, like arithmetically. You have to do a little less work. So if we take the circle equation, we plug in the center. So what you guys did is went off to the side and did this giant square root calculation for distance, right? And then squared it to get your radius. She's saying you can do the same thing if you take your x and y coordinates, kind of like when you write the equation of the line and you have like m, but you need to find b and you plug in a point temporarily to figure it out, then you can plug in those x and y coordinates that they gave you, which is doing the exact same work that your distance formula did, and is going to find for you r squared. So 9 plus -4 is 5, and squared is 25. 12 plus -5 is 7. Squared is 49. And if I can add these together properly, I get 74. So then I go back here, and my final version of the equation is that x plus 9 squared plus y plus 12 squared equals 74. Not 74 squared, because my 74 represented my radius already squared. Okay? Is that all right? Now, if you did the distance formula, you did the same thing. You plugged into the same formula using the same types of numbers. Okay? It just looked maybe a little bit different, and this might just look a little nicer without the giant radical and all that kind of stuff. Okay? Any questions about that? Okay, our last example of the day. You guys get 2 minutes to think about it, and then we have 3 minutes to make sure we have it right on our paper. Are you ready? All right, write the equation of the circle that has center at -6, 11. Again, a nice piece of information. But the only thing else they tell you about your circle is it is tangent to the y-axis. Maybe a picture would help. I don't know. You know.
Once, which means it has to be perpendicular.
Not that kind of tangent. What does it mean for something to be tangent to a circle? Like just touching it at one point, right? So the circle is doing that to the y-axis. Okay. Somebody tell me what you could immediately write on your paper. Eric, I don't want the answer yet. Somebody tell me what you could immediately write on your paper from the given information in the problem. Shannon. Okay, so r squared is the mystery, right? So we somehow need to interpret what the radius or the radius squared is, given that we're tangent to the y-axis. Claire.
I drew a graph and then I drew the center and tangent. Tangent means that a line goes through one point on the side, right?
Good.
So if it's tangent to the y-axis, then the radius is 6, so r squared.
Good. So this point's at negative 611 is what she's saying. And tangent means it just hits it at one place. And the place it has to hit at one point is over here. So my circle's going to be so ugly. Are you ready? Okay, I can't even finish it because of where it is. Just don't make fun of me, okay? Oh, it's actually going to go like, okay, yeah, okay. Whatever. All right, that's what's going on, okay? Laugh, I know, okay. But basically, if you know this is hitting at this one point, okay, and these are supposed to be horizontal to each other, you know that you can figure out your radius right there, and the coordinates of this point were negative 611. How far apart is this point on the circle to the center? 6 units. Okay? So the radius is 6 units long, meaning that our radius squared can just be represented with 36. Okay? Jenny?
I'm just wondering.
Yeah.
Like, could you, because the circle is tangent to the y-axis,
Uh-huh.
could you have plug in a second point for the x and y at 0, 11, because you know that
Yeah.
tangent and then solve it and get radius? I know it'd be harder and longer, but that's the best you can do.
Yeah. No, absolutely. And when you plug this point in, because you're going to have a 0 here and an 11 here, the part with the 11s is going to go away in your equation because 11 minus 11 is going to be 0. And you're going to be left with 0 plus 6, which is 6 squared will be 36. Okay? Yeah.